All right, folks. Just want you to all see if you see the Boston Dynamics person right here. Raise your hand if you see it. That way I know I've got it. All right, excellent. Now, I think it's good, even with things like Boston Dynamics, all these things, is to check in. We've talked about robots through the year in different times, but look at where they're going, and this has just been the last couple of years. So look at this robot. Watch this. No, this is a creepy one above. All right, this one and this one. I'll show you this one. Just like a dog. See how it switches its down? Hard to believe. Now this one I find a little bit crazy. This one I feel a little more creepier about. Watch this one. Not so much this. This still looks a little bit adorable and cute, but wait till you see. Oh, I can get the head of this thing in a minute. I can crawl in there like a dog. That's pretty cool. But look at that head. This is the thing I find just very unnerving to me. I find that particularly creepy. And they have, Atlas, which I'll just show them doing something here. It's pretty impressive. Look at this. Watch this. Mind you, it wasn't that long ago. It was a big success. We could get robots to walk up steps. Now look at that. All right, I'm going to go ahead and stop that. Let me just go see any questions here. Hello, everybody. Some people just came in and said hello. I'm saying hello back. So I think it's not a bad idea for every year, go and see what these new robotic companies are doing. This, to me, is mind-blowing, a little bit freaky. But that's pretty much still a lot of hardware. They're using some AI. Today, we're going to get into AI in a big way. Pardon me. I'm going to go ahead and show you a video. Now, this Thursday is middle school lab, but this Saturday is high school. All right? So We didn't because of, I believe, the holidays. Let me ask you this. How many of you got your, received your little LED and the microphone for your Raspberry Pi? You should have gotten them, guys, but I just want to make sure. We sent them home with a bunch. I want to see what group if didn't get it. All right. So let me see here. Raise your hand. I know you got them, William. Abigail, did you guys get these? William Zoe, did you get it? Raise your hand if you got it so we can get moving on here. I don't want to spend the rest of the time here. I'm trying to figure out. Caleb, let's go in here. I was here last time. Okay. I don't know if I did. Hannah? All right. Laura, what day do you have lab, Laura? And were you there at the last lab? Please type me down there, Laura. Let me see what you got there. I don't know if I did. Abigail did. Abigail, what day were you at lab? Was it a Saturday or are you on Thursdays? Thursdays or Saturdays, Abigail? I believe I had all the middle school guys got them. And I gave them out one Saturday labs too, so I'm trying to figure out whose is whose here. All right, so Laura, you did not get one. I go to Abigail, you did not get one. All right, this Saturday I'll get you one. All right, what group did get them though? Well, Caleb, you're on Thursday nights, right, Caleb? Yeah, and I got mine. Great. All right, I'm just making sure. I thought the only group I thought was a Saturday. I couldn't figure out remember which one. I didn't put it in my notes. I guess I should have done that. All right. Well, we're going to hand those out. Please bring your Raspberry Pi with you Saturday so we can build your Watson robot. All right? All right, great. So let's go ahead and do this. We're going to go ahead and show this video. I normally don't show a whole video in this class, but this is a pretty good thing for how Watson works. I like it. Now, one thing as you watch this, I want to point out to you, Watson is really good about text, reading text. I'm going to show you another, we're going to get into another longer in-depth AI. It's by NVIDIA. They're big into visual recognition, so that's their push on this. But this gives you text from Watson. And remember, we have AI, then inside of AI is machine learning, and the leading edge machine learning is now, you'll hear it called deep learning, neural net paths, Watson. These are all what we call deep learning, okay? You're going to see why in a minute. Okay. So, let's go ahead and watch this.
IBM's Watson is at the forefront of a new era of computing, cognitive computing. It's a radically new kind of computing, very different from the programmable systems that preceded it, as different as those systems were from the tabulating machines of a century ago. Conventional computing solutions, based on mathematical principles that emanate from the 1940s, are programmed based on rules and logic intended to derive mathematically precise answers, often following a rigid decision tree approach. But with today's wealth of big data and the need for more complex, evidence-based decisions, such a rigid approach often breaks or fails to keep up with available information. Cognitive computing enables people to create a profoundly new kind of value.
Cognitive computing is all part of this too. So there's some of these terms that are thrown around, neural networks, cognitive computing. They're similar enough that we're going to use them. What you're going to learn is we can, as a programmer, anticipate every possible solution or even every combination. And then if you think about combinations of solutions, we just can't do it. So we have to develop a way for the computer to start to learn these things. And that's what this is all about.
Value, finding answers and insights locked away in volumes of data. Whether we consider a doctor diagnosing a patient, a wealth manager advising a client on their retirement portfolio, or even a chef creating a new recipe, they need new approaches to put into context the volume of information they deal with on a daily basis in order to derive value from it. This process serves to enhance human expertise. Watson and its cognitive capabilities mirror some of the key cognitive elements of human expertise. Systems that reason about problems like a human does. When we as humans seek to understand something and to make a decision, we go through 4 key steps. First, we observe visible phenomena and bodies of evidence. Second, we draw on what we know to interpret what we're seeing, to generate hypotheses about what it means. Third, we evaluate which hypotheses are right or wrong. Finally, we decide, choosing the option that seems best and acting accordingly. Just as humans become experts by going through the process of observation, evaluation, and decision-making, cognitive systems like Watson use similar processes to reason about the information they read. Watson can also do this at massive speed and scale. So how does Watson do it? Unlike conventional approaches to computing, which can only handle neatly organized structured data, such as what is stored in a database, Watson can understand unstructured data, which is 80% of data today, all of the information that is produced primarily by humans for other humans to consume. This includes everything from literature, articles, research reports, to blogs, posts, and tweets. While structured data is governed by well-defined fields that contain well-specified information, Watson relies on natural language, which is governed by rules of grammar, context, and culture. It's implicit, ambiguous, complex, and a challenge to process. While all human language is difficult to parse, certain idioms can be particularly challenging. In English, for instance, we can feel blue because it's raining cats and dogs, while we're filling in a form someone asked us to fill out. When it comes to text, Watson doesn't just look for keyword matches or synonyms like a search engine. It actually reads and interprets text like a person. It does this by breaking down a sentence grammatically, relationally, and structurally, discerning meaning from the semantics of the written material. Watson understands context. This is very different than simple speech recognition, which is how a computer translates human speech into a set of words. Watson tries to understand the real intent of the user's language and uses that understanding to possibly extract logical responses and draw inferences to potential answers through a broad array of linguistic models and algorithms. When Watson goes to work in a particular field.
Okay, let's stop there real quick. All right, put this down here. Let me back up here just so we can look at this a second. When he's coming in here, in fact, I'm going to back it up just so you kind of see this. You observe something, right? Then you interpret that result and you test a hypothesis and you repeat it again before you make a decision. When you look at something, you look at what it is, you ask a question, you test your hypothesis, before your decision. Now imagine if these 3 things were repeated over and over and over again. This final answer would become more accurate. All right, so that was part of what they're doing there. Now, and so Watson is looking at all these different pieces of information to give this stuff context. See that? So it's not just a tag. It's not one tag. It's actually providing a series of questions. We're going to get in this a little bit more as they do it. Now, and this is why, English languages is so hard, because she's blue, right? But it's raining cats and dogs. Why do they have you fill out, I love this line here. Let me play this. Yeah.
We can feel blue because it's raining cats and dogs while we're filling in a form someone asked us to fill out.
That's confusing for a computer. It's confusing for us. Why? How? Another classic one is, I burned up my house. Nothing was left. It was burned down. Wait a minute, you just said you burned it up, burned down. Your feet smell, but your nose runs. Right?
It reads and interprets text like a person. It does this by breaking down a sentence grammatically, relationally, and structurally, discerning meaning from the semantics of the written material. Watson understands context. This is very different than simple speech recognition, which is how a computer translates human speech into a set of words. Watson tries to understand the real intent of the user's language and uses that understanding to possibly extract logical responses and draw inferences to potential answers through a broad array of linguistic models and algorithms. When Watson goes to work in a particular field, it learns the language, the jargon, and the mode of thought of that domain. Take the term cancer, for instance. There are many different types of cancer, and each type has different symptoms and treatments. However, those symptoms can also be associated with diseases other than cancer. Treatments can have side effects and affect people differently depending on many factors. Watson evaluates standard of care practices and thousands of pages of literature that capture the best science in the field. And from all of that, Watson identifies the therapies that offer the best choices for the doctor to consider in their treatment of the patient. With the guidance of human experts, Watson collects the knowledge required to have literacy in a particular domain, what's called a corpus of knowledge. Collecting a corpus starts with loading the relevant body of literature into Watson. Building the corpus also requires some human intervention to cull through the information and discard anything that is out of date, poorly regarded, or immaterial to the problem domain. We refer to this as curating the content.
So you got corpus, that's your content. You bring in human beings that help you get rid of that doesn't really work. That's not correct. So you get this big data. And remember, most data that we have in this world is unorganized. So you can write computer programs to help get rid of that, a little bit of that. You can use humans, but you get that core cleaned up a little bit.
Next, the data is pre-processed by Watson, building indices and other metadata that make working with that content more efficient. This is known as ingestion. At this time, Watson may also create a knowledge graph to assist in answering more precise questions. Now that Watson has ingested the corpus,
so all that's ingesting. I don't know why they're getting into the things, but all they're doing is now Watson has organized it, which is pretty cool because that would have used to been a human job. It's doing that. Okay. Don't worry, Jean-Marc. We're talking about AI. I remind you. Okay.
it needs to be trained by a human expert to learn how to interpret the information. To learn the best possible responses and acquire the ability to find patterns, Watson partners with experts who train it in using an approach called machine learning. An expert will upload training data into Watson in the form of question-answer pairs that serve as ground truth.
So they're doing France. This is going to be the core. We're just starting to ask all these questions. And so it starts to learn all these things about France. Like the Eiffel Tower. Where's French wine grow? Bordeaux wine. All right. The monument. All right.
This doesn't give Watson explicit answers for every question it will receive, but rather teaches it the linguistic patterns of meaning in the domain. Once Watson has been trained on QA pairs, it continues to learn through ongoing interaction. Interactions between users and Watson are periodically reviewed by experts and fed back into the system to help Watson better interpret information. Likewise, as new information is published, Watson is updated so that it's constantly adapting to shifts in knowledge and linguistic interpretation in any given field. Watson is now ready to respond to questions about highly complex situations and quickly provide a range of potential responses and recommendations that are backed by evidence. It's also prepared to identify new insights or patterns locked away in information. From metallurgists looking for new alloys to researchers looking to develop more effective drugs, human experts are using Watson to uncover new possibilities in data and make better evidence-based decisions. Across all of these different applications, there is a common approach that Watson follows. After identifying parts of speech in a question or inquiry, it generates hypotheses. Watson then looks for evidence to support or
So it's literally going on. It comes up with a hypothesis, and then it starts doing research to see, does it support or do I throw it out?
refute the hypotheses. It scores each passage based on statistical modeling for each piece of evidence, known as weighted evidence scores. Watson estimates its confidence based on how high the response is rated during evidence scoring and ranking. In essence, Watson is able to run analytics against a body of data to glean insights, which Watson can turn into inspirations, allowing human experts to make better and more informed decisions. Across an organization, Watson scales and democratizes expertise by surfacing accurate responses and answers to an inquiry or question. Watson also accelerates expertise by surfacing a set of possibilities from a large body of data, saving valuable time. Today, Watson is revolutionizing the way we make decisions, become experts, and share expertise in fields as diverse as law, medicine, and even cooking. Further, Watson is discovering and offering answers and patterns we hadn't known existed faster than any person or group of people ever could, in ways that make a material difference every day. Most important of all, Watson learns, adapts, and keeps getting smarter. It actually gains value with age by learning from its interactions with us and from its own successes and failures, just like we do. So, now that you know how it works, how do these ideas inspire how you work? How can Watson make you a better expert? What will you do with Watson?
So they're writing APIs so you can start using this thing. Now, it's a great video. I think it's a good video to give an overview. Now we're going to do a deep dive a little bit more into Watson, but then we're going to go into AI learning as all. Wednesday, we're going to go into GitHub. Then with time to tell Mr. Toy. And then the next week, we're going to just be setting up our Watson robots. All right? So that's kind of a layout of what we're trying to do. So let's go back to here. All right. So, and you're going to be kind of amazed. You are probably older. You are probably older than Watson is. Well, you are older than Watson. Well, I have a research project. You might be. I should say Watson is you may be older than Watson, but it's just started right around your age. All right. Now Watson made fame, and your parents will remember this, by beating Jeopardy champion. Watson's also going on to pass the medical test that all doctors are given. So if you want to be a doctor, you got to pass this really challenging test, and Watson did it already. You know, he's as smart as a doctor. Who knows? All right. So that all happened in 2011. August, they start marketing it for both healthcare and financial services, and now it's cross industry. So you can use it in lots of different things. Okay. What caused this to happen? Why do we have Watson now and this deep learning or cognitive learning? Well, it's a lot of things. One, we had the cloud. Big, huge server farms can process stuff. All right? Where Watson might reside, shall we say. We have you all and myself carrying computers on our hands and phones. We're using it all the time. And since we're always sharing on because of social media, well, there we go. And then you have the Internet of Things. So we have that connected to all of our devices, which is pretty amazing. Okay? You know, I think Dig is the one I'm used to. All right. Now, they're going to talk about it from a business perspective. It's IBM. They're talking about it, but some of this stuff is true. We're doubling information in an incredibly nutsy component. We had 90% of the world's data was created in the last 2 years. That's mind-blowing. Now, most of the data is useless. You know, it's thermostats everywhere giving you what the temperature was in your house, you know, every few seconds. Well, that bit of data, do you really need to know that? No. But we use it. 80% of the world's data is unstructured. When we get into that, is Structured data would be something like you saw lines where you filled out a form and you have your first name on one line, last name on another line, street number on one line, name of the street, zip code, city, state, that kind of thing. That's structured. I can search that. It's what we're used to. We can do it on a spreadsheet. Unfortunately, it's not how the world is. It's 80% unstructured, like you see with the written word. So that's where IBM's strategy was at. Okay? But with all this data, we're only using 20% of it. We certainly could be using it more to get stuff done. Okay? So, what they did is, and here's the thing, IBM stresses natural language and human communication. It evaluates what it's reading, evidence-based hypothesis, checks out what it's reading, does it back up with the data behind it, and comes up with an answer. And then adapts and provides it for the user. You know? Give you an idea. Back in 2012, they had 6 instances deployed in the last 12 months back then, right? 90% of the nurses, when given watching recommendations, would follow them. Now they're saying 75% reduction in time market with new cancer therapies. We'll see. But give you an idea how smart this thing starts to get. It's already did, by 2012, it already had read 2 million pages of text. 14,007, the data from almost 15,000 clinical hours, and reviewed 25,000 training classes. By the way, the machine itself is getting smaller. The one that was on Jeopardy, again, a lot of parallel processing power. It was the size of a small room. Now it's bigger than your desktop computer, but not by a lot, and it weighs about 100 pounds. All right? So you can see all these different ways we're using it and what makes it possible. I'm not going to really, but I just want to finish up with the Watson stuff here right now. Is you had the tabulating systems, and IBM, the people who made IBM, made all their money in the beginning by coming up with tabulating machines. So the census that used to take 8 or 9 years to do, they did it in months and saved the federal government a ton of money. That led to IBM. IBM International Business Machine, and they did all these tabulators. We then made them programmable electronic in the 1950s, and now in about 2011 we get cognitive. That's getting the computer to think like we do, and the way we're thinking on this stuff. We're going to get into that, what that means here in a minute. Okay? Now let me just do a real quick poll here. How's my pacing so far on this? Don't worry, Jean-Marc, days my computer hasn't working. All right. So we have 79% voted. Can we get some more people to vote here? And we can. All right, 86%. I'm going to go ahead and close the poll. Oh, 100% voted. Thank you. Share the results. Most of you said pacing is fast. Is good. All right. Okay. Now, pardon me. We're going to talk for the next 15 minutes or so, 20 minutes or so, about, let's talk a little bit more about deep learning. And this is also gets into cognitive. So if you have AI, you have machine learning, now we're talking deep learning or cognitive learning, okay? Now, I'm going to show you this. It's a little bit of video, not very long, 2 minutes. Understand, this is put out by NVIDIA. And then they have some associations with Google. I think I may be NVIDIA bought by Google. Lord knows that Google's buying enough stuff. But here we go. We're going to hit this.
It all begins from a single origin, a unique point in space and time. This is the spark of innovation that fuels your most amazing breakthroughs. It's a passion for discovery that unveiled the genesis of all that exists in the universe. Today, the power of AI helps computers achieve superhuman capabilities in image recognition and lets scientists save our most precious resources by
Oh,
analyzing
sorry.
in 1 month
Ah,
what
darn
used to
it.
take 10 years.
Back to the backup. We don't.
All that.
Sorry.
This is the spark of innovation that fuels your most amazing breakthroughs. It's a passion for discovery that unveiled the genesis of all that exists in the universe. Today, the power of AI helps computers achieve superhuman capabilities in image recognition and lets scientists save our most precious resources by analyzing in 1 month what used to take 10 years.
是谁发明了机械计算机？
Everyday devices translate even the most complex languages from voice into text and images into words.
Xavier is now present.
Helping the visually impaired recognize an old friend, or letting a blind woman read to her child for the first time. Autonomous vehicles give us the freedom to reimagine our city streets and travel where there are no streets at all to help the lost find their way home.
By the way, today it was in one of the magazines reported AI is now flying drones better than we do. So the drone, it's not even drone operators, the AI will fly better than we can.
We see robots teach themselves to perform simple tasks. We even watch in awe as they take their first steps. And today, a 2,500-year-old game meets its match as a computer competes with one of the greatest human champions of all time and wins. This is the collective imagination, fueled by forward-looking technologies and the beginning of your most amazing discoveries yet to come.
All right. Okay, they get a little carried away there, but you can kind of see. So there's this, we talk about different ways you collect data. One is text. That's IBM's guy. For visual recognition, you're going to be looking at NVIDIA because clearly they know a lot about video and cards, etc. All right. Let me go here. Sorry. There you go. I don't know how I pumped it. Now, if you don't think it's a fad, think again. Think of, I would say there's artificial intelligence. Then I would go with machine learning, and then deep learning or cognitive learning as being the most, it's the current leading edge type stuff. Now, this is Google Trends, how much interest we're in these things. And it's really starting to take off. For example, number of publications that we're talking about deep learning in China and the United States. Look, 2008, 2009, there are practically none. In 2015, there were 350 published in China, 200 published in the United States. And then you have the rest of the country. So we're leading. That's an indication of how much research you've done. That's why we care about that. The Computation and Neuroscience Conference growth, total number of registrations, 3,755. 2016, it jumped up to 5,000. So it went from nothing. Here's all these workshops, conferences, and tutorials. How many, look at those we're going through here. Now, Google clearly thinks this is the case. Now, these deep neural networks, come back, remember this image in a minute, because we're going to use this in a few moments. To give you an idea, at Google, how many people were using AI? 2012, there was nearly, hardly any at all. 4 years later, there were almost 2,700 projects using AI. So you go from, right, this amount of investments going on in the 216. So a lot is going into AI. And I bring all this up because if you have a parent or a friend or family that is an older friend of the family and they've heard about AI, which I have, there was always AI, it's right around the corner, it's going to change everything. And the fact of the matter, it wasn't. It really wasn't. It's only that all these new technologies, we've gotten to a perfect storm for doing this. So, all these areas are saying they're going to use AI. But remember with the IBM thing, it's only when we had this, hang on, let me show you what I'm talking about right here. Sorry. This. We have the cloud, we have mobile computing devices, everybody's using them, we're sharing them socially, we share the data we get, we're also connected to Internet of Things. All that's coming in, plus we have a whole field of big data that all aids in this as well. Okay? I keep doing it again. Why did I do that? Oops. All right. So input any kind of data we're getting in, be it text, be it sensors, be it images. Then we use artificial intelligence in the middle of it, and then we output it based on that. So that doesn't really add a whole lot of knowledge here, but let's get into the next things here. Artificial neural intelligence. This is machine intelligence that exceeds or equals or exceeds human intelligence at a specific task. So you can teach a computer to play checkers and beat any human being going. A very specific task, it's got it made. What we want to move beyond that right now, we're at the AGI side where applied intelligence to any problem at a human level value. Let's go look at a problem. It doesn't have to be specific to one thing, i.e. checkers. Superintelligence says it's much better than we are, including creativity and wisdom. This is a long ways away yet. All right, don't. And that's why IBM says you got to work with them both together. All right, so now. So what do you do on this to get this to work? Well, you have labeled data that is organized, and you give it a machine learning algorithm. So it tests those things. It's remember what we saw with France. You go out and say, I teach the computer, the Eiffel Tower is located in France. I ask it that question. It goes out, reads through everything and says, yes, I have these sources telling me the Eiffel Tower is in France. I'm 98% certain that's right. What's the answer? Eiffel Tower. That confirms it. The next time you ask it, is the Eiffel Tower in France? It looks at all the data I just had, plus it looks how it responded in the past and increases the percentage. I'm now 99% certain the Eiffel Tower is in France. Okay? Just like in sciences, we'll almost never say things for certain, but the computer's learning to do this. Okay? So once you've created that model, then you can start giving it raw data. Using the model it's taught itself, it can start to make predictions. And there's all kinds of ways of doing that. We'll get to that in a minute here. So let's do, and please, I'm going a little bit here, make sure there's no questions. So, all right. If you got a question, just go ahead and type it in there. You haven't, so do other people. Think of it this way. I'm going to use AI to help me with spam, which Google honestly does. So in the beginning, when you're trying to teach the AI to look for spam, you're going to have emails that have something in them that you can alert the AI to look for, i.e. asking for a checking account. You're going to automatically mark that as spam. If some of those strangers' checking account, then I'm going to mark that as spam. All right? So it's labeled. The email has to have the word spam. I've told the computer. Unsupervised learning says it looks at all the spams you've gotten in the 2 months. And it says, I marked all these letters as spams. What are other things that are similar in these letters? And then I'm going to use that and add that to my understanding of what spam is. This is something we would do. And then it reinforces it. When you click on it and you say, this isn't spam, it should learn from that, oh, I was spamming something that shouldn't be. Or you've just deleted everything I said as spam. That makes sense. If it's spam, you don't want it. That makes sense? So, but it does it over and over, thousands upon thousands of times in just a few moments. So it gets much better. And so we can make a regression. We can use a line. We can figure out, we can predict what's going to happen. What's really cool is anomaly detection, where it's unsupervised. It just notices there's an anomaly and tells you that. Clustering works this way in Wikipedia of something, where just simple text classified, predictive. You said a hurricane is a anticyclone. Well, that's supervised. That's a relationship. A dog barks. Classified. Again, it's when you find unsupervised things that are together. Did you know that, for example, in like a health issue, men in particularly in the Southeast get kidney stones. That's kind of a clustering thing. We wouldn't know it, and we just read it as an anomaly. All right? Let me give you some more here. So think about the response and application, and when you do it. This is basic machine learning, and then we're going to get into deep in a minute. So, a picture. Is there a human face? 0, 1. Yes or no? Loan application. 0, 1. Yes or no? Add plus. Did they click on it? Yes or no? Those are yes or no things. You can also provide an audio clip. You take an English sentence, convert it into a French sentence. We're getting much, much better about that now. Sensors from your hard disk, plane agent. Is this about to fail? I know people right now that have heating and air conditioning. The heating and air person came out to their house without them calling them, saying, you're about to have a failure in your system. Usually we don't find out about failures in heating and air until we stress the system. It's really cold outside. It's really warm outside. Right? And then you have cameras and other sensors. All right? And again, picture, that's photo tagging. You see that all the time. Loan approval. This is a little bit nervous. We got to be really careful. Unintended consequences. We got to write really smart algorithms, or we can get one group of people, you can get biases in there. That's not good. All right, add plus, target online. You got speech, language, translation. Again, getting better and better. These are some of the machine learning algorithms, comparisons, classifications. We're not going to get into that. That's what I think this one. Wait a minute, let's go back to this. Pull up. This is a linear. This is back in 2009. We use it all the way along. The guy came linear support vector machine. That was just in 2009. That's unbelievable. Some of you were 4 or 5 when we're just starting to use this. Now it's getting used all over the place. All right, let me go back around. That's where linear SVM. All right, decision time, everything else. All right. All right, so what is deep learning? And this is going to follow more like humans want and thought. And AI people for years have claimed, wanted to do. Let's use our brain. That's a perfect model. The issue always got to be with that is we didn't have the computing power. So that's what's changed. So what is the parts of the machine learning field? Learning representation of data. Exceptionally effective at learning patterns. A hierarchy of multiple layers that mimic the neural network of our brain. So it's going to use the layers. That's why I had that Google slide. I'm going to show you that in a minute. if you provide it tons of information, it begins to understand and do useful things. So the key is all you got to do is provide it lots of information. Well, who can do that? Certainly can be Google. So this is a deep neural network. This is the first thing we're going to see, and then we're going to pass it down to this network to make a decision. I'll show you exactly what we're going to do. So, human being, when you see something, when you first get the light images going, remember, you don't really see with your eyes, you see with your brains. But the data from your eyes goes in your brain. The very first ones are really just very crude. Is this bright? Is this dark? Is this a color? Is it moving? All going in there. But then it goes deeper into your brain and takes that image and turns it into something you understand. You know, and the strength of these connections is your long-term knowledge. Now, so you start with this cat. What your brain starts to see is very crude, but it gets more and more organized that it becomes a cat in your brain. So, you know, starts out here, goes here, here. Now it becomes something you think about. A deep neural network consists of a hierarchy of layers. That's what we're talking about here. Layers in the brain, for example. That analogy, but it's obviously in a computer, not in your brain. And transports, each layer transforms the input data into more abstract representation. So this is just very much zero on, off, and colors. By the time you get to here, it's a cat. So here's the edges. Here's nose, eyes, and ears. Here's faces. That's how it learns faces. This is why you see in so many big cities now, especially in Europe and probably in the US more, where they have this face recognition software. Is amazing. That's why when there isn't an attack in a big city anymore, they just start going through the cameras to see where the people were. All right. All right. You have input data, then you as the programmer have to keep adjusting so it gets better. Now with deep learning, you're not doing any adjustments. So, how's it used? All right. Well, speech and audio, computer vision, natural language processing. But again, not surprisingly, language, computer vision, speech, audio. That's why don't get wound up like AI's, you know, you're going to be the Terminator rising up anytime now. It's just not going to happen. Computers first started seeing things in 1958. We could start to recognize handwriting in 1998. You know, that SVM and the restriction Boseman's machine, those things that people have developed, 95, 2006. Google Brains project, they take a cat brain basically, and they look at the number of neurons in a cat brain, and they try to put it into a computer. Huge energy requirements. All right. The Computer Vision World Cup. How well can computers see things? And this is the number of errors. This is human performance. They now get fewer errors than we do. So if you really want to witness at a trial, it should be a computer. All right. Word error rate and speech recognition. When you hear speech, we're still better, but it's closing in. Look at the improvement from 2000. Kind of didn't really change a whole lot, and things have stepped up. And now with this machine learning, it's now 2015. Look how the level of performance. You want this to be lower, and you want this to be below that black line. And you know, it's the same things we've been talking about. You know, computation, big data, those things. Here are the big players in it, by the way. Not surprisingly, Amazon, Google, IBM, NVIDIA, Facebook. Here's all the startups. All right. So, what you're trying to do is the input layer is the very first initial. That's just collecting the sensor data. And then we're going to keep testing things. And these layers, the data is all being passed back and forth between these layers. And you've written code that looks at the probability of you're testing a hypothesis with each one. and the probability you're right, and puts it all together, and it comes out 1 point as an output later, with a percentage saying, hey, well, we think we're right. And this is not really a surprise. You do that with our brains. We'll never catch our brains without doing linear thought. All right? Let me go ahead. So, deep learning, it's more like this. You give it sample data, you forward it through the networks to get a propagation, you back propagate these errors and update the connected weights and do it again. So that's all really fancy smancy way. Using this, what you're doing here is you go through the network. When it gets it wrong, you update the probability so it gets better at predicting this. So let me see if I can get something up here that would work. There's all these different tools and models for imaging things. All right, so all that's way of saying is, let's see if I can get what I want. Let's just bag it. That's just a fancy way of saying, remember if we did an iteration, you said this Eiffel Tower is in France, and you check it and you say, yes, it's in France, and it goes on and collects the data. If it gets it wrong, that's also included in there. So right or wrong, we're learning more, just like we do. That's why people always think, well, scientists want their hypothesis to be right. I would argue not really. We just want to know that our test is testing our hypothesis. And in fact, when the people did the Higgs boson, when they were taking the subparticles and slam them into each other, some of them were kind of hoping we wouldn't get the results they got. The results they got was what they predicted math-wise. If it was something new, that would mean, wow, we don't really understand it as well as we thought we did. But let's go back to here, so I digress. And these start to get into, you have autoencoders, you can go into a lot more level into this. And then this is visual data and a convolutional neural network. And it's using visual systems just like we do, depth, height, and width. And it's giving you probabilities on that. So, convoluted layers detector automatically learns to filter out needed information from input by using convolution kernel. Pulling layers of computers the max or average value of a particular feature over a region of the input, downsizing the image, helps us to take something that is very concrete and make it very very abstract. Now, there is a whole list of stuff on this that you can get going. And it's a shame because you would almost like to, I wish we had endless time to go through it. All right, but you can kind of see that this gets, if you like math and you like programming, even if you don't like math, this is an exciting field to be in right now. You imagine combining that with cybersecurity, so we start to learn how the attacks are coming. What's the likely attack? Be a very powerful thing to do with that. Does anybody have any questions? If I go farther, then I got to go to a big deep dive, and then we'll really be here for a while. All right, let me do one more thing. You can go to GitHub and do these next things. If you haven't registered for GitHub, please do. All right, we've got 9% voted. Please vote, folks. 77, 85. All right, 5, 4, 3, 2, 1. The same 5% found it interesting. 25% said it okay. I'm just going to tell you this. I don't see AI going away. I don't think it's here to stay. We have hardly anybody knows how to program in this. So it's a great opportunity for you, especially for those of you that are about to go head off to college soon. I can't stress it enough. Okay? So with that in mind, I'm going to go ahead. Remember what I said. I believe Saturday. Let me go back and check on the calendar. Let's take a real quick look on this. All right, so there we go. High school lab, make it this Saturday. 7th and 8th grade lab this Thursday. You don't have lab this Thursday, be the next Thursday after that. Okay? Make sure you bring your Raspberry Pi. And you can bring the hat if you want. All the things you did with your Raspberry Pi. Don't worry about keyboards or monitors. We have those. And that microphone type device. And the, I'll provide you that, the microphone and the RGB chip. You can make your watch and robot. Okay? All right, everybody. Let's take care. Okay? Bye-bye. Take care, everyone.